Organizations deploying generative artificial intelligence into production environments immediately confront an operational paradox. Traditional computing relies on relational databases. A deterministic query locates a specific row and column, returning exact data. Large language models use transformer neural networks differently. A prompt triggers a probabilistic computation, predicting the most likely sequence of upcoming tokens. This distinction defines the nature of an AI hallucination. It is a strictly mathematical phenomenon, not a cognitive failing or a software bug. Generative models are designed to optimize for statistical plausibility. If the network is unsure of the facts, it will still generate a highly confident, perfectly fluent sequence of words that happens to be entirely fabricated. In the high-stakes environments, an uncalibrated model that confidently fabricates a regulatory clause or hallucinates a phantom liability on a balance sheet creates severe legal and financial risk. Because this tendency to fabricate is hardwired into the architecture of next token prediction, it cannot be eliminated with a single patch. Reliable enterprise AI requires a structured, multi-layered engineering stack. Design's baseline reliability is dictated by the raw text corpora it processes during pre-training. To reduce early hallucination risks, engineers execute rigorous data cleansing protocols. By systematically filtering out toxic parameters, duplicated documents, and synthetically generated noise, developers ensure the network builds its foundational understanding on a mathematically stable dataset. Once the base model understands language, it undergoes fine-tuning to shift from simple text prediction to following specific user instructions. A standard method for this is reinforcement learning from human feedback, or RLHF. A separate algorithm, called a reward model, evaluates multiple outputs generated by the LLM and scores them based on human preference. The network updates its internal weights in response to these scores, favoring factual accuracy and helpfulness. However, RLHF carries a specific vulnerability known as reward hacking. Because humans naturally prefer authoritative, well-structured text, the network learns to adopt a highly confident tone. This learned fluency can successfully mask subtle factual errors, tricking the evaluator into rewarding a hallucination. Static weight adjustments establish a necessary baseline for behavior, but they cannot provide the model with real-time updates or access to proprietary, domain-specific facts once training concludes. To solve the problem of outdated information, the middle tier of the stack shifts the computational focus to the exact moment a user asks a question. Retrieval Augmented Generation, or RAG, bypasses the limitations of static weights by actively connecting the model to verified, dynamic external databases. The architecture operates in a specific sequence. It begins the moment the system ingests the user's prompt. The prompt text is mathematically converted into a numerical array called a vector embedding, representing its semantic meaning. The system then runs a similarity search inside a vector database, scanning millions of pre-indexed embeddings to find the data points mathematically closest to the prompt. The system extracts those highly relevant document chunks and injects them directly into the language model's context window, alongside the original question. By forcing the model to generate its response based solely on this verified external data, RAG immediately neutralizes contextual hallucinations caused by outdated training data. For enterprise deployments, this approach allows organizations to enforce data access controls at the retrieval layer and ensures the final output includes traceable citations pointing to the exact source documents used. RAG guarantees the facts are current, but the system still relies entirely on the model's internal logic to interpret and synthesize those facts without introducing contradictions. To verify that internal logic, we move to the top tier of the mitigation stack, deliberate execution. Traditional LLMs operate on rapid, intuitive processing, instantly generating the next word. Modern reasoning models are engineered for deliberate, methodical problem-solving. They achieve this through test-time compute. Instead of immediately outputting text, the system pauses to allocate computational power specifically for internal verification before presenting an answer. Through chain-of-thought prompting, the model is forced to break a complex problem into a sequence of transparent intermediate steps. Advanced implementations use the tree of thoughts framework. The model actively explores multiple potential solution paths simultaneously, mapping out different logical approaches. To navigate these branches, the system employs a process reward model, or PRM. Standard outcome supervision only evaluates whether the final answer is right or wrong. A process reward model evaluates the mathematical integrity of every single intermediate step. The PRM actively scores the logic trace, penalizing mistakes the moment they occur. This forces the model to abandon a flawed branch and backtrack to a safe point before the error compounds. This aligns with the RACE framework, which evaluates both answer correctness and reasoning consistency. In regulatory compliance, an AI might correctly reject a fraudulent transaction, but cite an irrelevant legal clause in its internal reasoning. Arriving at the correct answer through flawed logic creates massive liability and destroys auditability. Reasoning models actively safeguard against this. By dedicating compute to process supervision, they ensure the entire logic trace is mathematically sound before the user ever sees the final output. The final operational step is binding these 3 mitigation tiers into a continuous, self-correcting workflow using AI agents. Within an agentic framework, the large language model serves as the central cognitive router. Equipped with memory and logic, the agent can autonomously identify gaps in its own reasoning, or recognize when it lacks the data required to complete a task. When it identifies a gap, the agent dynamically triggers external tools. It can pause its generation, query a database for fresh context, execute a script to verify calculations, and read the result. To aggressively filter out hallucinations, agents execute a multi-pass self-evaluation procedure. In the first pass, the model generates an initial chain-of-thought response to the user's prompt. In subsequent critique passes, the model is prompted to act as a harsh evaluator of its own initial output, checking for factual the temperature parameter during these critique passes to widen the model's token sampling distribution. This forced randomness prevents the critic from simply repeating the initial answer's logic, instead compelling it to consider alternative and potentially more accurate interpretations of the evidence. The agentic framework establishes the LLM as a modular component in a software system that prioritizes iterative refinement and autonomous logical verification over single-pass text generation. To see how this architecture prevents data corruption, we can observe the fully assembled mitigation stack resolving a high-stakes task. The prompt asks the system to extract a company's specific Q2 profit margin from a massive, unstructured financial report. A raw, unmitigated base model relies entirely on its static weights. If the exact figure is outside its context, it guesses, generating a highly plausible but entirely fabricated profit margin. When we pass that identical prompt to a fully stacked AI agent, the output changes. First, the agent recognizes the need for current data and triggers a RAG pipeline, successfully retrieving the latest verified SEC filings from the vector database. Second, the model dedicates test time compute to mathematically verify its extraction logic. It evaluates the numbers found in the retrieved text, cross-checks its own reasoning, and outputs the correct figure with a verifiable citation. This success is the result of 3 distinct engineering layers. The bottom tier provides a reliable baseline through rigorous data cleaning and human feedback alignment. The middle tier anchors the system to external reality, injecting current, verifiable data through vector retrieval. The top tier enforces mathematical consistency, utilizing reasoning models and agentic loops to supervise the internal logic trace. Reliability in artificial intelligence is a continuous mechanical process. It's a closed-loop system relentlessly working to verify data, penalize logical errors, and maintain computational stability. Complete elimination of statistical hallucinations is impossible in a generative network. But by isolating the root causes of failure and deploying targeted algorithmic controls, we can treat hallucination as a manageable operational variable, empowering us to build AI systems that are progressively more trustworthy and secure.